Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and today we're exploring a branch of robotics that looks nothing like the hard, metallic machines you might picture when you think of robots. Instead of stiff joints and rigid arms, imagine robots that are made of soft, flexible materials that bend, twist, and stretch, more like living organisms than machines. These are called soft robots, and they're part of a growing field that blends mechanical engineering, electrical engineering, and physics in surprising ways. Think about how your own body moves. Your muscles aren't hard like steel. They contract and expand. Your skin stretches without tearing. Even your heart pumps by squeezing, not by turning like a motor. Nature has already figured out an incredible design system for movement, one that's efficient, adaptable, and safe. Soft robotics tries to learn from those designs and bring them into engineering. This technology has the potential to revolutionize the way we interact with machines. Imagine surgical robots that move as gently as a human hand, underwater explorers that swim like octopuses, or wearable devices that feel more like clothing than machinery. By replacing metal with silicone, rubber, and other flexible materials, engineers are opening the door to a completely different future for robotics. In this episode, we'll dive into how soft robots actually work, the science behind their motion, the materials that make them possible, and the clever ways engineers power and control them. We'll also look at some of the real-world applications already in development, from medicine to space exploration. And as always, we'll consider the limitations that engineers are working to overcome and where this technology might be headed next. So let's get started. Welcome to the world of soft robotics. To understand what makes these soft robots different, we need to start with what they're made of. Traditional robots are usually built from rigid materials like steel, aluminum, or hard plastics. These materials are strong and durable, which makes them great for factories or heavy lifting, but they don't bend or stretch very well. That means a traditional robotic arm is powerful, but if you asked us to pick up something fragile like a grape, it would probably crush it, unless programmed with extreme precision. Soft robots, by contrast, are built from flexible, stretchable materials like silicone, elastomers, and hydrogels. Silicone is the same kind of material you'd find in bakeware or swimming goggles. It's soft, squishy, and resilient. Elastomers are polymers, long chains of molecules that stretch like a rubber band and then return to their original shape. Hydrogels are especially interesting. They're networks of molecules that can hold a large amount of water, making them soft, slippery, and even similar in texture to living tissue like your skin. By using these kinds of materials, engineers can make robots that don't just move like machines, but actually feel like biological organisms and can do things that traditional robots cannot. But materials are only half the story. The other question is, how do soft robots move, especially move with precision? Without motors and gears, what powers them? The most common answer is pneumatics, which means using air pressure. Imagine a balloon. When you blow into it, the rubber stretches and the balloon changes shape. Soft robots use this same principle, but instead of a simple round balloon, they design chambers inside the robot's body. When the air is pumped in, those chambers expand in very controlled and specified ways, causing the robot to bend, twist, or grip. For example, a soft robotic finger might curl around an object when air fills one side of it. Closely related is hydraulics, which uses liquids instead of air. The concept is similar. By moving liquid through channels inside the robot, engineers can make it flex or move. Liquids are less compressible than gases, so hydraulic systems give more precise control or apply stronger forces in specific situations. Then, there are shape memory materials, which sound almost like science fiction. These materials are metals that remember their original shape. When heated, their atomic structure rearranges, and they snap back into a programmed form after being bent. You can bend a wire made of a shape memory alloy, pass an electric current through it to heat it, and watch it straighten itself. Engineers are also using shape memory polymers, plastics that respond in a similar way. These materials let specific soft robots move without pumps or external air tanks. Instead, heat or electricity can make the material bend. Another approach involves electroactive polymers, sometimes called artificial muscles. These are plastics that physically expand or contract when electricity flows through them. They can mimic the way real muscles work, creating smooth and natural-looking motion. All of these methods of movement are based on physics, and it helps to understand a few key terms. When engineers design soft robots, they think about stress, strain, and elasticity. Stress is the force applied to a material. Strain is how much that material deforms or stretches as a result. Elasticity describes how well the material returns to its original shape once the stress is removed. For example, if you stretch a rubber band, the stress is your pulling force, the strain is how far it stretches, and elasticity is what makes it snap back. In soft robotics, engineers have carefully selected materials that can withstand large amounts of strain without tearing and have just the right elasticity to perform repeated motion. A big inspiration for this field comes from biology. Think about an octopus. With no bones at all, it can squeeze through tiny cracks, wrap around objects, and move with incredible dexterity. Despite this, they're also incredibly strong. Soft robotics have studied octopus arms to design flexible robotic tentacles. Another inspiration is the starfish, which uses hydraulic pressure in its feet to move across the ocean floor, almost exactly like hydraulic systems in soft robots. Even caterpillars offer lessons. Their soft, segmented bodies show how to crawl or climb without rigid parts. Nature, in other words, is the ultimate design manual. And this biological inspiration has already produced some amazing demonstrations. One famous example is the soft robotic gripper. Instead of using rigid fingers with joints and motors, this gripper is made of soft, flexible materials with inflatable chambers. When air is pumped in, it curls around an object. The beauty of this design is that it doesn't require precise programming for every single joint. Whether you give it a strawberry, an egg, or a metal tool, it naturally adapts the shape and applies just enough pressure without crushing or dropping it. By combining flexible materials, clever actuation methods, and inspiration from biology, soft robotics creates machines that move in ways that traditional robots never could. They can bend, squish, and conform to their environment. That makes them safer around humans, more adaptable to unstructured environments, and capable of tasks that rigid robots would struggle with. Right now, soft robotics is in a fascinating transition stage, moving out of the lab and moving into real-world application. What started as proof of concept demos with inflatable tubes and silicone grippers is now being used in hospitals, farms, and even underwater. Engineers are proving that robots don't have to be stiff, metal machines to do meaningful work. One of the most famous efforts comes from Harvard's Weiss Institute, where researchers are developing a robotic arm that's inspired by an octopus tentacle. Instead of hinges and joints, it bends and curls smoothly, letting it wrap around objects to have stronger grip and more precise pressure. Again, that allows it to grab delicate items, like a piece of fruit, without crushing it. Even more importantly, it can easily adapt its grip to whatever it encounters. While this is something rigid objects can do in some occasions, it tends to be much harder without the power of soft robotics. MIT has also been pushing the field forward with a robotic fish designed for underwater exploration. Built with soft materials and powered by fluid flowing through channels in its body, it looks and moves just like a real fish. That design makes it nearly silent, which allows it to blend in with marine life in ways propeller-driven machines can't. This has applications in studying marine biology, specifically by getting close to animals and plants without disturbing them out of their natural state. Soft robotics is also making its way into healthcare. Exosuits, which are wearable devices made from soft, fabric-like materials, are being developed to assist people recovering from strokes or injuries. Unlike rigid exoskeletons, these suits don't lock the body into unnatural postures. Instead, they work with the wearer's natural motion, offering just enough support to help someone relearn how to walk or regain strength. This approach is far less intimidating than strapping someone into a bulky metal frame, as well as being much more effective and comfortable. Soft robotics today is a field buzzing with prototypes, each one pushing the boundaries of what's possible. We're not yet at the stage where you'll see soft robots stocking grocery shelves or repairing your car, but the groundwork is being laid. The leap from lab bench to commercial product is happening piece by piece, and it's only a matter of time before soft machines start slipping into everyday life. These prototypes and applications we've already seen, robotic fish, flexible grippers, wearable suits, they're all just a starting point. The real question now is, how will these machines be used once they move out of the lab and into the world? Medicine is one of the clearest answers. Think about how delicate the human body is compared to the metal instruments surgeons use today. Traditional tools are precise, but their rigidity means even a tiny slip can cause massive damage, especially in sensitive areas of the body. A soft robotic tool, however, could bend and flex its way through tissue without scraping or bruising. It could be a surgical instrument that behaves more like a guiding hand than a sharp blade, or prosthetics that don't just attach to your body, but move like they were part of it all along. Soft robotic exosuits are already being tested in rehabilitation. And in the future, they could become everyday assistive devices, a lightweight sleeve that quietly helps someone walk or regain mobility after an injury. The same qualities that make these machines safe for the body also make them perfect for dangerous, unpredictable environments. After natural disasters, debris often leaves human rescuers with little access to trapped survivors. Rigid machines struggle in these conditions, but a soft robot could compress itself, wiggle through a crack in the rubble, and bring sensors, oxygen, or even food to someone in need. Instead of sending people into unstable wreckage, we could send in flexible, adaptive machines designed to survive in tight and shifting spaces. Agriculture offers another promising frontier. Large mechanical harvesters revolutionized farming for crops like wheat and corn, but delicate produce, like berries or tomatoes, still relies on careful human hands. Soft robotics change that by mimicking the gentle grip of a human hand, or even the curling motion of a plant tendril. Robotic arms could harvest fruit with almost no damage. On the larger scale, these robots could sort, package, and handle food in ways that reduces waste and lowers costs, also solving labor shortages in agriculture industries worldwide. Exploration, both underwater and in space, pushes soft robot engineering to its extremes. Oceans are high-pressure, corrosive environments where rigid machines break down quickly. Soft robots, made of flexible, resilient materials, are better suited to handle those conditions. They can maneuver through reefs or glide along fish without disrupting ecosystems. In space, the challenges are different, but just as severe. Spacecraft have limited cargo capacity, which makes packing flexibility a huge issue. Soft robot could fold completely during a launch and then expand into a functional form upon arrival, meaning that the packing isn't as big of an issue. On alien terrain, rocky, icy, or entirely unknown, adaptability may matter more than brute strength. A rover that can flatten itself to slide under obstacles or curl into a protective ball during dust storms might succeed where traditional machines fail. It's not just specialized fields that stand to benefit. Soft robots could eventually become part of our daily routines. Imagine a household helper that can handle fragile objects without breaking them, clean around children and pests without posing risks, or even prepare food with the same dexterity as human hands. The line between machine and furniture could blur. A chair that molds itself to your shape, clothing that adjusts to support as you move, or shoes that adapt their cushioning step by step. These aren't science fiction concepts. Researchers are already prototyping wearable robotic fabrics that respond to motion and pressure. Looking even further ahead, the boundaries between soft robotics and biology may also begin to dissolve. Engineers in Switzerland have already built a silicone-based artificial heart that beats like the real thing. It's not ready for transplantation, but it demonstrates that flexible materials can replicate the complex motions of living tissue. As materials and control systems advance, it's possible that future implants or artificial organs could be robotic, yet feel alive, functioning inside the body with the same softness as natural tissue. What ties all these ideas together is the shift in mindset, moving away from robots as rigid industrial machines and toward robots as adaptive, lifelike systems. Each potential application, from surgery to farming, from disaster zones to deep space, grows out of the same fundamental principle. Softness allows machines to move and interact in ways rigidity never could. The current prototypes may look simple, even fragile, but their future points toward a world where machines blend seamlessly into human environments. Not as tools we fear might break something, but as companions designed to work safely alongside us. That's the promise of soft robotics. Not just new machines, but a new philosophy of engineering. Even as soft robots promise incredible flexibility and adaptability, engineers face significant challenges in turning those possibilities into reliable, real-world machines. The very qualities that make soft robotics exciting, their pliability and resistance, also make them hard to control, power, and manufacture consistently. One major limitation is material fatigue. Soft robots rely on flexible polymers, elastomers, and hydrogels to bend, stretch, and compress. Over time, these materials can tear, crack, or lose elasticity. Unlike metal, which can tolerate repeated stress for decades, soft materials may degrade after just thousands of cycles of movement. Engineers must carefully select materials, optimize thickness, and sometimes add reinforcement, but no perfect solution yet exists, especially for robots expected to perform hundreds of repetitive motions in demanding environments. Another hurdle is control complexity. rigid robots behave predictably. When a motor rotates, the arm moves along a precise path. Soft robots, however, deform in multiple directions simultaneously. This makes predicting and programming their motion far more difficult. Advanced sensors, real-time feedback loops, and sophisticated algorithms are required to monitor the robot's shape and adjust actuation continuously. Even then, slight changes in temperature, load, or material properties can throw off performance. Designing control systems that are reliable, fast, and energy efficient remains a central challenge. Power and actuation present another set of problems. Many soft robots use pneumatic or hydraulic systems, inflating chambers with air or liquid to create motion. While effective, these systems often require pumps, compressors, or external reservoirs, which can limit mobility and increase size and weight. Alternative actuation methods, like shape memory alloys or electroactive polymers, often consume a lot of energy or respond slowly. Engineers must balance power, speed, and responsiveness while keeping the robot soft and lightweight. Scaling up is also tricky. Small laboratory-scale robots can be carefully fabricated by hand or using 3D precision printing. Making larger robots, the kind that may explore disaster zones or support human mobility, introduces new challenges. Maintaining consistent material properties across large structures, preventing leaks in fluid-based systems, and ensuring even actuation throughout the robot are all difficult tasks. Small errors become magnified in bigger systems, reducing performance or even causing failure. Finally, durability, and specifically environmental durability, remain important concerns. Soft robots are often sensitive to temperature extremes, chemicals, and sharp objects. A robot designed for underwater exploration may perform poorly in freezing conditions, while one intended for disaster zones could be punctured by debris. Engineers are working on coatings, hybrid materials, and redundant actuation systems, but, of course, no universal solution will ever exist. In short, while soft robotics offers unprecedented adaptability and new ways for machines to interact with the world, the field must overcome significant engineering challenges. Material fatigue, complex control systems, actuation constraints, scalability issues, and environmental vulnerabilities all need to be addressed before these machines can become a seamless part of everyday life. Yet, the progress so far demonstrates that researchers are steadily pushing the boundaries, making the promise of soft, lifelike robots increasingly tangible. Soft robotics represents a remarkable shift about how we think about machines. From the flexible, gripper-like arms that handle delicate objects, to robots that can crawl through tight spaces or mimic the fluid motion of an octopus. This field blends material science, mechanics, and physics to create machines that move more like living organisms than traditional metal robots. Now that we've explored how soft robots are built, how they move, and the bio-inspired principles that guide their design, we've also seen that while the field is advancing rapidly, significant challenges remain. Controlling flexible structures, preventing material fatigue, powering and actuating robots efficiently, and scaling them up for real-world application are all hurdles that engineers continue to tackle. Yet even with these obstacles, soft robotics is already making an impact. From experimental underwater robots to wearable exosuits and surgical tools, showing that these flexible machines are far more than just a laboratory curiosity. Looking forward, the potential applications are vast. Soft robotics could revolutionize medicine, search and rescue operations, agriculture, and even our homes, making machines safer, more adaptable, and better integrated within human environments. They blur the line between machine and life, offering a glimpse of a future where technology feels more organic, responsive, and human-centered. When robots stop being rigid and start becoming soft and lifelike, we're not just creating new machines. We're redefining what engineering can achieve. The promise of soft robotics is exciting, but its true power lies in the possibilities it unlocks. Machines that adapt, protect, assist, and interact with the world in ways we've only just begun to imagine.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.